Hello everybody, welcome for our last tutorial on extremes and variability, tutorial 9 on thresholds. This tutorial should recap almost everything, or at least let every concept that we had discussed sort of pass for you to have a really nice ending where you see the application of the concepts that we have worked with. Thresholds are how we can test some of the infrastructure that we have, or perhaps some of the risk that we're having due to climate change, and we can assess them, or we can test them based on some of the frequency analysis that we have performed. As an example, here you can see our record from Hoek van Holland and the 200-year flood period return levels that we created through first a non-stationary analysis and then secondly a stationary analysis. Let me start with that non-stationary analysis. As we have said before, it gives a very interesting image of the way that flooding developed, coastal flooding developed at Hoek van Holland. We see that in the first half of the 19th century, there were quite a bit of floods that almost stopped, and I think one there even does stop the 100-year level, whereas at the end, that doesn't seem the case anymore. A little bit of caveat is that we assumed a linear relationship on the location parameter, so it might be that that linear relationship is not really appropriate anymore for the end of our record. If you would have a close look at there, however, it does tell you something about how these extremes maybe are changing over time, and that even though they get really close to what we could consider a 100-year flood in a stationary analysis, the dotted line, because you see that that gets stopped by this line at the end of the 20th century / the beginning of the 21st century, even though that's being overtopped, it's not the type of extreme flooding that we saw before. And this gives an interesting perspective to this, right? Because when we build infrastructure, for example, to protect us to coastal flooding like here, it is based on a stationary frequency analysis, or at least it's based on a stationary return period. For example, we might want to build like a piece of infrastructure like a flood wall that can protect us for a 100-year flood. Then the 100-year flood will be that dotted line that you can see. It wouldn't be topped at the beginning of our record, but it definitely would be topped at the end of our record. And not because it's topped by a 100-year flood, but because it's actually topped now by a 50-year or maybe a 10-year flood. Something much more, or something much more or smaller that we would see given the new climate distribution that you find. So thresholds are very important, and thresholds based on stationary analysis can be problematic in a climate changing world. So let's give a bit of a longer example of this to really hit that down with you. We're going to look again at the Mississippi River. We started with that in tutorial 1, and we're going to end with it in this tutorial. You've seen this record before. It's a stream flow, annual peak stream flow record at the Mississippi River in Vicksburg, which is really at the end of the Mississippi, really down below. And we're going to look at some of the thresholds that are being applied around there. So the Mississippi River is pretty dynamic. I've shown you here on the left a map, which we call the Fisk maps. They are made by Dr. Fisk, which was a geomorphologist, a fluvial geomorphologist, who, based on sedimentary analyses, constructed these maps that show all channels of the Mississippi River. So every colored, like each of these colored ribbons that you see, is a previous channel going back thousands of years, which is a very impressive map. They look really beautiful. I really encourage you to look them up. So what we learned from these maps, or what we have learned from these maps, is how dynamical the Mississippi River is and how much these change. And that's not always to the benefit of society. For example, the state of Louisiana is very dependent on the Mississippi River as an economic artery. In New Orleans, many boats get in or out of the Mississippi to move goods up and down, and their trade is dependent on having this port, or much of their economy is. However, at the same time, the Mississippi River is discharging water, or if it were naturally managed, would be discharging water in the Atchafalaya River, which is some side channel in its delta at the end. Here, Louisiana wouldn't be happy about, because the Atchafalaya River moves more towards the west into Texas almost, meaning that New Orleans would lose basically its access to the river, leading to economic disaster, but also to a lot of flooding. So what they did is they built what we call this old river control structure, basically a flood wall, or at least flood infrastructure that only releases water into the Atchafalaya River, only so much % of total discharge, just to make sure that not all the water moves in there, meaning that the Mississippi completely changes its course. Keeping this flood protection in place is, of course, essential to the state of Louisiana and the city of New Orleans. However, in 1973, a flood almost toppled this system. You can see here the scoring that's taking place around the flood wall. And an event like that, or a case where the Mississippi will break through the old river control structure, will really cause probably an immense, what we call a Volscian event, which means that the complete river all of a sudden changes its direction, probably through the Atchafalaya channel. So that's something that they didn't want to have happened before. So they started thinking about what would be this sort of like maximum flood level that this old river control structure needs to keep in place with. Like, what is what they now call project design flood. The flood needs to be withheld. And in that case, you need to take into account climate change, of course. So this is the values that they came up with. Here you can see the Mississippi River in yellow and different places around it with associated to it different types of discharge. These discharges are basically, by the way, based on cubic feet per second and that times 1,000. Or in this case, divided by 1,000, of course. So you can see that the further we move downstream, the higher that threshold becomes, because of course more and more water is added. If anywhere along this, one of these thresholds is over the top, the old river control structure will be at serious risk. So we don't want to have that happen. Now, we had a record from Vicksburg, so we can take that number that's associated with Vicksburg and treat that as a threshold that cannot be overtopped by, say, a 100-year flood or 500-year flood or 1,000-year flood, whatever we think is appropriate there. So we take our threshold and we can, or our data from Vicksburg, and we can now apply this to a frequency analysis, both stationary and non-stationary if you want to see whether that threshold, that project design flood, is being toppled. Here you see two of those figures. On the left, you see a stationary analysis, and on the right, a non-stationary analysis. And in the dotted line, you can see the project design flood in now cubic meters squared per second, by the way. So let's start with that stationary one on the left. We see three lines, the yellow line being the observed data that you had seen before. And we can see that based on the observed data, the project design flood is not being crossed on a 500-year, 100, or 50-year flood. So that's pretty safe. That's really nice. And that makes sense because, of course, the water managers, the engineers that built this piece of structure took this into account. They had to look at the observed data to see how much they had to build for. If we, however, look at the blue at the red line, we see future model data. In this case of climate scenario RCP 8.5 and RCP 4.5. If you don't know what those are, they are related to these SSP scenarios, or the sort of the predecessors of these SSP scenarios, being RCP 8.5 being the worst case scenario, and RCP 4.5 middle down the road, if I make that easy. So RCP 8.5, there's a lot of carbon emissions from fossil fuels, and in 4.5, a bit less. What we see is that, particularly in RCP 8.5, the red line is crossing the threshold of the project design flood about a 50-year return period, meaning that the project design flood in the RCP scenario 8.5 is a 50-year flood. And that is a pretty high risk, probably, for a structure that's so important to the economy of Louisiana. So you see that climate change is already affecting the risk that we experience based on flooding, or the flood hazard you experience. Of course, we are assuming climate change there because we're using climate change scenarios. So we cannot use a stationary analysis. We have to look at the non-stationary analysis. And that's what we do here in the graph on the right. It's a little bit of an awkward graph. It looks a little bit strange, not like those straight lines that we have seen before with Hoek van Holland data. That's because it's dependent on temperature. So parameters of GEV distribution are related to tempered global temperatures in a linear trend. And that's why it looks a little bit off. However, you can still see that the red line, the RGP 8.5 line, crosses the threshold already in 2050. And this RGP line is the 100-year flood, by the way. So that means that the 100-year flood is being, or like the project design flood is the same as the 100-year flood in 2050. For RGP 4.5, the less climate change scenario, we see that that is reached about 2080. So quite a bit later already. So you can see the effect of reducing our carbon emissions on the risk that it takes on these for flooding on the Mississippi River. For all your information, the black line that you can see there relates to the secondary y-axis on that graph, which is the return period of the project design flood. So how does the project design flood change in return period over time, if that makes sense? You see that the uncertainty on it is really, really big. I'll talk about the assumptions that I made here in a second, but you can see that it really moves from a 1,000-year flood all the way to close to a 30-year flood in the end in 2100. So that's a pretty steep decrease over time, which should be really troubling given what we see. So what are some of the assumptions that were made based on this analysis? Because I want to make clear to you, whenever you're doing these types of analysis, we know that extreme data is very scarce. So we need to take in the assumptions to really know the value of the analysis that we did. It doesn't mean, given that they're assumptions, it doesn't mean that we shouldn't do these analyses, because they are important to indicate the risk that we have given climate change, but we need to be aware of the assumptions. So here again, we assume that parameters will remain non-stationary into the future, and in this case always be related linearly to temperature. That might not be the case, that might change, or there might not even be a linear relationship with temperature or time in general. So this is something that you should be aware of when you look at it, and you might want to check other models too. Secondly, we don't know if the GEV distribution is a good fit at all. Perhaps there were other models or other distributions that would fit much better. The normal distribution or Pareto distribution or something else. You want to check for those too, and you learn in tutorial 4 how to do that. Then secondly, we can look at the model that was used to get this flooding data. So these RGP 8.5 and 4.5 scenarios are based on a model, of course. And this was not only a climate model, because climate models don't predict flooding, they predict things that happen in the atmosphere. So this was a whole coupled Earth system model, a very complex model with a very, very much different components that has a pretty high resolution still, especially for things like flooding. So you can really doubt or put some uncertainty about some of the values that we get from these types of models, because there are so many factors involved. You need to really assess these models locally or build local models to get good data out of them. So this is something that you want to take into account. Well, what is your input data for some of these future scenarios? And then finally, I want to just make you aware of the many different thresholds that you could think of. Of course, we talked about infrastructure right now, and there are different types of infrastructure that you could think of. Also things like energy system, how long does how much sea level height can a offshore wind farm, for example, handle, or what types of waves. Those are things that you can assess. But on the other hand, also things like health. And here you see a piece of coral. Corals bleach at certain temperatures, so that's a threshold. So you can use temperature records to see what the return periods are for these bleaching events, or, for example, on human health or something else. So there are many different ways in which you can apply these extreme value analyses. And that leads me to only say thank you for staying with us this entire day and doing all the tutorials. I hope you enjoyed them. I hope you learned quite a bit. This is a very important topic. And if there's anything that you want to ask further, or if you want to reach out, you can always email us. My email is here on the top, jbreinders@lec.univ. Or you can reach out to Matthias, who created these beautiful tutorials that you have done together with me. He would always be happy to answer any of your questions or chat to you if there's anything else that you want to discuss with us. Thank you again. Hope you learned something, and perhaps talk to you another time.